Okay, 3, 2, 1, clap. That's how we're gonna do it. 3, 2, 1, clap. You're supposed to say clap.
Are we?
No. All right. So now that we're all synchronized, we are gonna now begin talking. So we're continuing this kind of series on the classes at Advanced Security. This one, we are going to be talking about the upcoming so it's March 2nd when we're recording this, and the next upcoming live class on Advanced Security is the Introduction to Hardware Hacking and Reverse Engineering. So that one, so that's what we're going to be talking about today. What this class is, who's it for, what you're going to be doing, kind of the fun stuff we got planned. So, Dimitri, why is this a class? Like, what's the deal with this thing?
Well, Josh, I mean, I don't know how it was for you, but I mean, getting into hardware is kind of a stretch. I mean, if you have more of a software background, so it's not always trivial. It's kind of a steep climb. It's not easy. I mean, it's very different. And so, just as an example, I mean, the example that I always like to think of is getting somebody to the point where they're using GPIO. They're writing to memory mapped registers that then do something in hardware. And kind of once you grasp that and you understand how that works, then everything else falls into place. So whether that be FPGAs, where you're actually building the hardware peripherals that you're working with, or I mean anything else hardware related for the most part. I mean, I always feel like that's a kind of a pretty good like introduction. I mean, once you grasp that concept, it kind of opens the floodgates to appreciating all the other hardware topics. So a lot of people come to us and ask, I mean, so the typical thing that people say is, hey, I have a computer science degree, as an example, or, I studied some other, computer related degree, computer security or what have you. I'm not that familiar with all the brand new InfoSec degrees and whatnot. But for the most part, people kind of feel, I didn't study computer engineering. I didn't study electrical engineering. What can I do? I'm not used to, I haven't touched hardware in the past. And I mean, I guess kind of part of this conversation is also to show you that that's not an uncommon path. I mean, I don't know how you got into hardware, Josh. I'll happily comment as well.
Yeah, I mean, I remember because I started off computer science. So the first, I mean, we learned C++ at the Naval Academy. So I think they started off with that. And then at one point I did Java when Java was cool because, you build once, run and everywhere. And that's still apparently what they say about Java. So, but then I definitely remember when like the concept of like writing a driver was like, oh, that's like black art kind of stuff. Like, how do you like I can get it from a serial terminal from like dev TTY, but like, how do you this magic of actually talking to this driver thing was was completely black art. Like no idea how that worked. It was just like a software abstraction at that point. It just comes in as if you think of Linux as like with the biggest hardware abstraction layer, I mean, that's basically what it is. It's like a giant HAL. And once you have it in a character device, I mean, you largely don't care. And so how all that stuff worked was, I remember like being completely mystified at one point. So, this is kind of, I think what we're trying to do with this class is really show how that works at like the lowest level, right? To get really throw away all these layers of abstractions, because that's all programming languages are, just lying to you about how the actual computer works, right? It's just fake abstractions, because at the end of the day, like it's you're hitting the CPU registers, right? And so we're throwing all this away and going there. So we have some neat ways to do that, I think, which I think would be pretty fun.
All these new kids running Node.js to be closer to the metal. I mean, closer to the metal or something else.
Yes. Yeah. Well, it's interesting to see on that topic, it's interesting to see like what the interpreter languages of popularity are, right? So I would argue that like Circuit Python is certainly making it. So this is Adafruit. So there's Python, Then came MicroPython, which was Python on microcontrollers, and then CircuitPython is Adafruit's kind of take on MicroPython. And then right, so this is like very popular in the maker world. It's actually, to be fair, it's one of the quickest ways to get a board that supports. So we'll talk about that in a second. A board that supports MicroPython or CircuitPython. If you have that, like the new ARM, like the new Raspberry Pi Pico, it's the quickest way to blink a LED, because you bring it up, you get the terminal. It's usually like LED.blink, and it's like, oh wow, like I'm actually doing something. But like, I mean, I looked at this for both, like for this class and for some other like product related things, at like the survey of interpreters that are available, and consider things like eLua, MicroPython. There was a bunch of other ones. So Scheme, Tiny Scheme, because I'm a Scheme fan. So look at Tiny Scheme, and then fourth. And so like the conclusion that I came to, I mean, so fourth is to spoil it. I mean, that's the one we're using for the class. And why are we resurrecting a 50-year-old programming language? And it's like, so this has been on Hackaday and stuff before. So I mean, there's other hardware people using Forth, but it's pretty much like interpreted assembly. I mean, it is what you want when you're trying to do this low-level thing. So I mean, pause here, because otherwise I'll keep ranting on Forth. But I mean, we did look at I mean, there is, yeah.
I mean, we'll give you ample opportunity to rant on Forth a little bit later. I mean, we'll open the floodgates to Forth and let you rant on that. No, but I mean, it's all valid points, right? I mean, so lots of people, I mean, so for example, I got into hardware kind of because I was modding my gaming consoles back in the day for obviously entirely legal reasons that no one would ever have any issues with. And so I got interested in like, what are they actually doing? What kind of man-in-the-middle bypass are they doing at a circuit level on the PCB? And I started looking into that. So, I mean, the Xbox modding scene was pretty epic back in the day. I mean, which is all well documented in Bunny's book for the most part. We'll give you a taste for it. So, I believe it's called Hacking the Xbox.
Yeah, I think it's free now, actually, too.
Yeah, it is actually. That's a good point. So you can find the PDF. I mean, No Starch kind of. I think it's No Starch was the publisher, but yeah, it is free as a PDF online. Totally worth the read. Totally gets into like what hardware hacking and bypassing security can be. Kind of if you implement all of it. But I just remember, I mean, I did a computer engineering degree, and I remember we did zero practical stuff in my entire degree. I mean, so for people who think that you do, like just because I have a CE degree, I have all this background in, talking to hardware, understanding protocols, etc. I mean, wasn't a thing. And so kind of when I got around to teaching or in doing a PhD and kind of getting into chip hacking and all the lower level stuff, or at least kind of that having sparked my interest in realizing that I need to understand everything that happens. Before that, I found myself with an Arduino. I mean, that's literally how I started. I was sitting there with an Arduino, playing around with it, understanding what happens. And I mean, I think before we get into interpreted languages, I mean, which definitely are way easier and way more approachable. I mean, there's also nice tools. I mean, obviously, the Arduino. I mean, the popular ones I'd say top three list would be Arduino, Teensy, and Raspberry Pi, which kind of all fit into different product slash hacker maker segments. I mean, the advantage with the Arduino, I just remember, is you just start with the Arduino IDE, which is kind of limited and has all these weird macros for speaking of the I/O, speaking of peripherals and whatnot. And essentially, I mean, I would say I think everyone that I know that does hardware nowadays has gone through this phase where you start with the Arduino IDE, and after about a week, you're at AVR GCC, just writing bare C scripts. I mean, I call it scripts because I mean, every time you do embedded, I feel like it's not like you're actually writing a program. I mean, like a serious quality program. It's always like you have a main function that calls everything. I mean, is like the YOLO way to write embedded code. But yeah, but so you find yourself, I mean, so you basically figure out a way to not use the Arduino hardware because you want the PCB, but not to use the Arduino itself, and kind of to get away from that and to be able to toggle everything directly. But at that point, turns out you're writing C, which I mean is always a topic for discussion on various electronics forums and other
Yeah,
other
it's
podcasts.
yeah. It I mean there's multiple way. I mean, I don't know. Yeah, this is coming. I think we've maybe even touched on this before, but like the fact that there's multiple different on-ramps here, like because I did stuff with SparkFun a few years ago, and they did definitely are catering to the maker movement and Arduino. So I mean, I guess with all of them, all these IDEs, Arduino, CircuitPython, all this stuff is, objectively very nice. The problem comes in, I think, when you want to do something that's not supported by it, right? So if your project, can be done with the teensy, can be done with this, can be done with Arduino, can be done with CircuitPython, and you can use that board, then then you're fine, right? That it's supported, you can use it. There's no issue there. When you start then trying to port something to a new platform, unless because all of these are basically written in C under the hood, unless if you want to do that kind of stuff, if you want to then take that and move it down, and even like I remember, one thing that I think came up on the Arduino IDE is like their I2C driver, for example, would do I2C read and write, but there was a limit in the actual IDE of how big the buffer was. And so for the chip that I do a lot of stuff with the AT-ECC, sometimes the I2C commands can be over 100 bytes, and Arduino would be like, nope, you sent more. Why would you send more than 64 bytes over I2C? I'll just silently drop your write is what it would. So I think it supports it now, but you would keep writing and then it would just drop the bytes. So so this is the trade-offs with them. They're objectively good. But I do feel, I'm not, I think I'm not trying to shit on them any particular more so than anyone else is doing. But at some point there is it does feel like there's a certain outgrowing of those kind of languages.
No, but I mean, it's definitely way more approachable in a way because you load it up. The IDE has all these example projects, and I mean, you just run Blinky dot Arduino or whatever their file extension is, and then it's already blinking an LED. And now you're like, wait, let me blink this other. Let me instead toggle a GPIO. And turns out you use the same code and get it up and running. But what I mean, I remember the kinds of stuff that like blows your mind and that you find yourself stuck at. I mean, I don't remember how good the Arduino wrapper is, but like a typical example would be if you're dealing with GPIO on hardware. Well, you have this general purpose IO, you have a direction register, you have to set which direction is the IO going, and so just picking arbitrarily, taking the code, doing copy paste, and picking a completely different pin means that it's not going to work because you probably didn't configure, even though the code should work as is, you haven't actually done the second step, or kind of technically like the initial step of configuring the IO to talk to the outside world. Just that as an example, I mean, the kind of stuff that you're missing. So, I mean, not to mention all the protocol stuff, which we'll go into as well. But basically, I mean, this is the kind of stuff that we're going to be talking about in the class as well, and picking people up from. I've only written programs that I've compiled with GCC on my computer, and then ran a.out from the command line versus how you actually get it and run it, or kind of how you actually manipulate signals and send data over serial protocols and on an embedded system.
Yeah, and I think also for the security aspect of this is that you always kind of have to go one layer below to attack the layer that you're trying to work at, right? So in order to and so that's kind of like the focus of this class. So we're trying to take you down to that GPIO toggling register layer, so that you can, when people look at and evaluate serial protocols and drivers and the classic. This is why they're still. I think at the end of this, you'll have an appreciation why there's all these bugs in drivers still, because there's it turns out that there's all these little edge cases, and sometimes it's not trivial, and when you try to do thing at like a big bang level to really understand how the protocol is working, you'll definitely, I think, have an appreciation for how bugs can develop in drivers and why it's sometimes very difficult to get those right. And then, I mean, that's like I mean, I think the Linux kernel is doing better these days. But I mean, this was like, I remember like the first time someone was like, oh, let's take a look at the C code in these kernel drivers. And then it was like the blood was dripping from the walls after that inspection. This is kind of, I mean, this is why.
But I mean, it's also, I would argue it's not only that, because it's not just like the driver side. I mean, it's also how does the data look over the wire? I mean, what can I manipulate? I mean, so for example, you have something like, if we're talking about SBI, you might have something like a chip select. So it turns out, anyone who can get their fingers on this board can control that chip select and can prevent something from getting read or written. I mean, the opposite of that would be, or kind of not the opposite, but in I2C, the common one is there's a bunch of hard-coded addresses that you would use in general. So any address that appears on the wire that is not that one will, corrupt kind of the behavior of the master and slave. So you can inject data that way, etc. So, I mean, we're going to be covering the common serial protocols in this class as well, and kind of having everyone manipulate them and kind of generate the signals. And so, I mean, I would say, like, if you're trying to interface to hardware, the starting point that you end up in, and I mean, I guess this would also kind of be a opportunity to talk about this versus the kind of the previous iteration of the intro class. I mean, so initially, kind of just with pandemic, etc. I mean, it's been hard to get hardware. I mean, like, that's also an aspect of why we're revamping this class. So we want to make sure that people can actually go and buy a single piece of hardware and run everything on there. So no wires need to be connected or anything like that, because for people who are new, that just adds to the learning curve without really offering them anything beyond frustration. But having said that, the thing that you always find yourself in, whether you're playing around with an Arduino and some target, is you sit down, and I mean, it inevitably happens if you're doing anything security related. What you're doing is you're sitting and you're trying to manipulate, the ones and zeros that are flying over the wire. So essentially, what you need to figure out how to do is, how do I get an interface to be able to manipulate the ones and zeros and to kind of knock them out over the wire and have them appear for the whatever I'm interfacing to.
Yeah, and so I mean that can be so you brought up I2C. That's a classic one where I've had a problem with, where even if you're trying to do, I mean, so if you try to, so one way to do this, you could say, well, I'm going to take this microcontroller, it's got a hardware I2C peripheral, and I'm going to try to man in the middle this I2C bus, or I'm going to try to do this attack on an I2C bus with like a typical microcontroller. One of the problems you can come into, because it's something that's happened to me, is that sometimes the I2C peripherals are actually too smart for their own good, right? So I've had, especially with I2C, where you can have multi-masters and there's bus arbitration. So if you start doing these kind of attacks, in one of the peripherals I worked with basically kept saying, as we would try to inject things, it kept saying there was bus arbitration losses, which basically it thought that there was another master on it, which there was, right? And then it would generate the interrupts. And so like it was really quite painful to try to use. I mean, so the entering argument was, let me just write the C driver to talk to this I2C peripheral to do what I needed to do. But the hardware was actually getting in the way, because it was not designed to do a security attack. It was designed to talk to a temperature sensor and get the data back. So, I mean, these are things where like you sometimes would have to like then drop down and say, all right, I need to do this more directly with direct access to the bits on the wire, like you said, where otherwise you're going to be prevented by by the silicon that you have.
Right, but it's not. I mean, it's not just like a slave that you're talking to as well, right? I mean, it's even at a C level, like from the point of view of writing and using the peripheral as it was designed by the component manufacturer. Like they won't let you do stuff that doesn't fall in the spec. And so, I mean, I know, because that's kind of the niche we fill in, as people come to us and ask, how do I send data that is not in spec? And turns out you have to write something from scratch is inevitably the answer.
Yeah, for sure. So that's kind of the I guess I think that pretty kind of sense of like the why of like why we're kind of doing this, and this is the approach to this class, is right to give you the ability to Yeah, I mean, the summary would be like they give you the ability to send bits on the wire for whatever protocol you're trying to do, right? So this is, and then once you know that skill, then you should be able to take it for obviously the protocols that we show, and then adapt it for whatever protocol that you need. Like I think that's the goal out of I don't know, what would you
No,
how
exactly.
does that sound, Dimitri?
No,
Yeah.
I mean that sounded perfect. I mean, so looking at wires with something like a logic analyzer or an oscilloscope, actually seeing them and then being able to reproduce them from code that you actually control, being able to write code that actually goes out over the wire and reproduces those signals. Hence, you're able to inject data, manipulate data, and do all those things is a big deal. I mean, and that's kind of the key. I mean, that's the on ramp to all hardware hacking, I would argue, and even I would even argue not only hardware hacking, but even forward engineering and building. I mean, just like truly understanding the basics. I mean, you gotta talk to have one piece of hardware talk to another piece of hardware. That's when kind of everything falls into place for understanding how systems communicate. You pop open some consumer device and see a bunch of chips, and like how does it boot? Where does the data come from? Where does this data flow? What would the data look like in theory if like I could tap this line and look at it right now? So gates are wide open at that point. I mean, once you've gained that understanding, and so just to touch like where you can end up with this. I mean, so the forward engineering. I mean, so Josh teaches some of the classes, some of the other classes with how to integrate stuff like secure elements. So the one that we talk about uses I2C interface, and then with so for example, a lot of my classes focus on using FPGAs, and so there we're actually writing custom peripherals from scratch. So if you did want like a high performance interface, something that was not limited by the kinds of limitations that we're going to talk about when we get into interpreted languages versus running. I mean, being as close to the metal as it gets, i.e., running Verilog code on a FPGA. So somewhere in between there is I mean, you gotta pass the on ramp to get on this highway of doing all this hardware related stuff.
See, the goal is first we get you on the on ramp with this class, and then by the end of the class, you're going to be surfing AliExpress for cheap electronics to add to your cart, because that's probably one of the things that'll slip out during the class as well. Is how to buy basically a how to on navigate AliExpress for the best electronics.
I mean, let's just say we had a good call about all the amazing things you can get on AliExpress today, and even we were amazed. I mean, and we have a pretty high bar for things that would surprise you that you can order on AliExpress. But yeah, I mean, it's kind of funny. I mean, AliExpress. I mean, we were discussing this in our call today as well. I mean, it's ironic that people do security and they don't look at AliExpress, because I mean, you'd be surprised how many devices there are for dumping other devices that are good to go.
Yes.
On AliExpress, where you just click buy. You have to wait. The penalty is you have to wait 2 weeks until it gets to you, but then you're good to go. It does it all in one click.
Yes, yeah. It's the anti-Amazon in terms of speed, but in terms of availability of odd electronics, it has Amazon beat for sure. So yeah, on that, because I am like on switching topics to like what you're going to be using in the class. So we are, like Dimitri mentioned, basing this on the Xilinx Zinc part. The board that we're going to be using is the one from Digital. I'll show it up on the video for anyone who's listening in. I'll just have to describe it as a nice, pleasantly white board with a zinc on the. And it's not going to focus for me. Nope. But yeah, you get that was a fail. But but yeah. So on AliExpress, you can find somebody made a bunch of zinc dev boards that then the product must have failed, or they're a bad run or something. Because the zincs are not a cheap chip, but on AliExpress you can buy them from $10. With a Zinc 7010, which is one of the smaller Zincs. But the problem is it doesn't have like a power supply and all this other stuff. But if you want to just collect a bunch of Zincs, there's someone who made these dev boards. Then they're flooding the market. they're flooding the market with zincs on AliExpress, $10 zincs. So some people claim that they were the old Bitcoin miner. So the Antmain, which is the like number one ASIC manufacturer, they use zincs on their control board so that their control board is a zinc, which then is controlling their ASICs for the miners. And so anytime they make a new version of their Antminer, AliExpress gets flooded with zinc control boards from the previous generation Antminer. So that I've picked up some of those before. They're pretty good, but they're only the 7010s. So again, it's the smaller one. And then you need like a PCIe connector. I know, yeah, they need a PCIe connector to power. So it's not like the most convenient thing, but I mean, a $10 zinc board is arguably a pretty good deal. Yeah. So the benefit then, so in this class, so we're going to be using the zinc, which gives us the benefit of both providing. So everything's going to be an SD card image, right? So other things that you would need is an SD card reader writer with a micro SD. No need to splurge on the micro SD. I think I'm topping like the image I gave Dimitri for testing the other day was maybe like, I don't know, it was like in the megabytes. Okay, so don't. First of all, this board can't do more than a 32 megabyte
gigabyte
or 32 gigabyte. I mean, no, that's already don't even know these gigs. Right, so they can't do more than a 32 gigabyte micro SD. So don't buy a big one. And then also, like, come on, we get so much information on that thing? Like, it's you don't need that much in your pocket. Okay, I bought about 5 years ago. I bought all the USB sticks I'd ever need. They're all like 4 gig, 8 gig, and that's it. That's it. You're done.
And we find out about this because Josh runs out of room on his USB stick.
I mean, you just gotta. I mean, apparently you can. If as long as the dump was all zero, so you can compress it, fine. But then I eventually found my external hard drive, so I was okay. But I mean, why do you don't need that much information on a USB? What are you carrying around? You carry around all this data on a USB stick.
I mean, the smallest. I'm pretty sure last time I'm pretty sure the last time I was ordering SD cards, the Samsung SD cards. I'm pretty sure 64 gigs was cheaper than 32.
No, I like to overpay for my flash, but I'd get SLC flash, right? The single bit per cell, and I'll pay $60 for the 4 gig, and I'll be perfectly happy. I like to overpay for my flash memory. Not dealing with this MLC,
CNC technology.
No, just 1 bit per cell. That's all it should be. That's it.
I mean, makes sense.
Yeah. So the benefit then of that nice zinc is that then we can both do a Linux image and I mean basically anytime you pop in so we'll be providing you the images and then you flash them down, and then that board can either look like a Linux board, it can look like a microcontroller. I mean that thing, the IO on one port will be sometimes it'll be SPI, then you pop in a different SD card, it'll flip. I mean, so we have it's not surprising. I think we talked about this in the last episode about intro to FPGA. FPGAs are used in education because I mean it's like a Play-Doh. You can basically mold this thing to whatever you want. So we're going to be using this, and then so the tool that we're building, right? What we're building out of this thing is the kind of the debut, if you will, which we're debuting here. The beginning of what we're going to be calling our like embedded hacking platform. So everyone in the InfoSec community, of course, knows of Kali, and then it's great. It's a Debian-based package, right? It has all sorts of tools. I mean, like I definitely use it. I know lots of people use it. Quickly download the ISO. You got all the tools installed, and that's really, really good for doing like network pen testing and this kind of reverse engineering at kind of like the software level. But it's not. While they do have an ARM build for Raspberry Pi, it's not really geared to the kind of stuff that we're doing. So so basically what we're announcing is that we're going to be making, based on the Zinc here, a platform for doing that kind of stuff, which we're calling Spearf1sh. But it's got a 1 instead of an I, so you know it's LEET. So that's how you know it's for offensive research, because it's got LEET in it. So this is in this class here. What you're going to be using is essentially the Spearf1sh platform to do this kind of low-level attacks. And so we're going to be building upon this platform, not only in this class and other trainings as well, to kind of provide the tools there. We'll have that's part of the motivation to have the interpreter in the FPGA to kind of give you dynamic access to some of the the IO that's on the FPGA, because I mean we could have it's basically like a microcontroller is attached to a Linux platform, all kind of in one silicon. So so that's kind of the super exciting other announcement with this class as well.
No, for sure. And I mean, so for people who are new to hardware, I mean, the advantage is we can, with such a platform, I mean, you're going to order one board, and first of all, we're going to teach you low-level hardware using this board, and second, you can go ahead, load our kind of Linux image onto there, and this will come pre-installed with other tools to sniff. I mean, do stuff. I mean, we're planning to do stuff like build logic analyzers, data loggers, stuff like this. I mean, so I mean, the irony was Josh and I were discussing this, and I mean, usually the conversation is like, what's the minimal? I mean, so let's say we want to do something like put some ones and zeros on some IO line, and usually the conversation goes like, let's take this microcontroller, or in my case, I mean, it's usually I usually say, let me write something in Verilog for the FPGA, and then never ever does the conversation go into, but why don't we just use Linux attached to this thing? And then we kind of realized that we actually have a class where we built Linux for this exact platform.
Yeah.
So we actually do have Linux for this thing. And so somehow, without realizing it, we've come full circle and accidentally built Linux, which means that it's now easier to build all our embedded hacking, hardware hacking tools running Linux than it is to make them run something else, essentially.
Yeah, and then the other thing is that what's nice is that, like, because we're using this, just, it's this digital board, right? So this, I mean, there's no, you don't have to wait for a pre-sale. It's already available because with the the digital, we're building on this platform that Digital made to start with. So I mean, it's a pretty epic. Like, there's the risk of hardware bring up is zero, as you would be typing out in the risks of crowdfunding, because the hardware already exists. So it's just, yeah, once you have because Linux, while it's great for all the reasons that Linux is great for having this like standard HAL and having all the tools available, what it's arguably not great at is trying to directly manipulate bits, right? Because like, you could do it obviously via the sysfs GPIO, but then it's like, and then yes, I know, I'm aware there's like real-time kernels and stuff like this, but I mean, ultimately it's like, please, Mr. Linux kernel, when you get around to it, I'd like that bit flipped. Thank you. And then it's like, actually, now I have to run, I have to run my systemd log cleanup. So I'll just flip your bit in a second once I get around to cleaning up systemd. So I mean, these are the problems. I mean, so this is the problem. And then Beaglebone. I mean, so there are platforms that try to do things like this. Beaglebone is probably the one that comes to mind as the closest, because it has two embedded real-time units and on the chip, and that support has gotten better. I haven't used it. I mean, when I was doing a lot of Beaglebone stuff, it was like still pretty painful to compile to do things for the real-time unit. So like essentially, and that was one of the push to kind of get an interpreter going on this. So essentially you have a real-time unit in an interpreter, so you can kind of get, we're trying to get you the most of both worlds, where you don't have to compile something, flash it. You can just basically kind of change it on the fly. So that's why we have.
Was it painful because you didn't have a 24-core EPYC server for just building Linux all day?
I mean yeah. So Dimitri knows these more than I do, but like the benchmarks for apparently CPUs is building Yocto Linux, right? And so like when you actually do, we do Yocto development, and it is a pain, right? So it's like the first time, especially the first time you build Yocto, it's like, okay, let me start this in the morning and I will plan in the afternoon to do some work. I mean, it does take that long, which is also why I'm a fan of Buildroot, because Buildroot, I think even on this EPYC server that I have, I think that image takes like less than a half an hour. I don't know the exact time, but like it's reasonable. If you do it on a 2-core VM, it takes like 45 minutes to an hour to build Buildroot, which is, yeah.
So yeah, if they want to see this, we'll definitely add it to the advanced security GitHub. The Buildroot, and give you an opportunity to build it from scratch. If you guys have the support already, you want to play around with it. Essentially, we're going to be using that as the hardware for all the stuff that we have coming up, and essentially kind of building out this platform. And we'll kind of have to see how the pieces fall in place. I mean, I do think you should mention that kind of the downside of using a Zinc, though, Josh, with the compile times there.
What? Oh, first of all, there's no downside to Zinc, but there are some annoyances. So the one is if you are trying to, so obviously, if you want to modify, so we're going to be, the Spearf1sh SD card will have a built-in Bitstream. And one of the things we are doing is we'll probably ship it with multiple Bitstreams. So you can right now at compile time, you could probably change, hey, I want this port, I want to use this hardware. If you want to change that, you totally can. It's obviously then you have to know some about Vivado, and then when you're doing things with a Vivado, then you have to that takes a while. And then the other kind of complication there is because we're using a microblaze as the embedded microcontroller. Then that workflow of building a Bitstream. To be fair, I do it. This is basically the 2-day class. So this is the 2-day class on Zinc, is to go through this workflow because it's a little complicated. So like you have to make the Bitstream, you make a microblaze, you have to get code working for the microblaze, and then you have to go back to your Bitstream, embed the code in the, and if you don't know anything about how Zinc works, I appreciate this is a lot of information, but you then have to do this whole workflow to get that working. But I mean, you totally can change the Bitstream and the stuff. Like it's going to be otherwise an open hacking platform.
So yeah, no, for sure. And I mean, the goal is really going to be to just have the tools installed to give you an easy way to boot different firmware. Let you boot different FPGA images, etc. So we're kind of gonna look to build out those examples because I mean the feedback always is from a lot of people. I mean, I'm one. It took me a while to I kind of converted myself back to using Python plus libftdi, which is just a nice wrapper around the FTDI. And now we're kind of going back to running, an even more hardcore embedded Linux platform, running a full-blown Linux. But you get a lot of advantages like Ethernet and all that kind of stuff. So, I'm excited on all the courses to come. We don't have it up yet, but this year, right around July, August, so the typical Black Hat weeks, we'll probably have a 4-day class just on hacking stuff using this. So teaching people how to use this as a hacking tool, hacking platform, looking into different different types of hardware, etc. So look out for that. So that'll hopefully be up at some point as well. But let's talk about interpreters now. So just as a topic.
Oh, yeah.
I mean, so kind of it's a means to an end. On the one hand, is you need a way to run code, but so I think it would be worth mentioning just for everyone, just like what the footprints are of different interpreters, because I do think that's what the footprints are versus the memory sizes that are typical in embedded systems on the one hand, and then on the other hand, just shoot.
Yeah,
go for it.
Right. So like I said, there was a few reasons I was looking into this. The obvious advantage is that then, the thing that everyone hates doing is basically board bring up, right? So because typically this is involving the vendor's IDE, trying to get a hello world, compiling it, flashing it. And so arguably, objectively, this is actually kind of like the pain. And this is why, most silicon vendors try to make this on-ramp as easy as possible. So it's like, all right, well, I don't want to go through that. So is there some, magic way where I can just type on this thing and have it work? And so that's an interpreter. And then, so the options are the MicroPython, eLua, Forth, which is one of the unconventional options, I think. But then, the two biggest ones, and then there's some weird
unconventional is putting it lightly.
It's okay. It's fine. Here's the thing, right? Like the programming language thing ended with when they made Lisp, right? And then everybody after that just basically stole the ideas from Lisp. And everyone's lucky that I didn't try to, because Tiny Scheme also works. I got Tiny Scheme going, but then I was like, some people can't deal with the parentheses.
Everyone watching
And
this should know that Josh uses Emacs and I use Vim.
yes. So unfortunately, on that note, Spearfish, if I want Emacs to run, I have to do some porting because it's a little big, but Vim will work out of the box with Spearfish. So
Classic Vim win.
Micro Emacs, which apparently was what Linux uses, that's available. But I tried Micro Emacs, and I don't even know why it really has the term Emacs in it because it's not. The key bindings are not close. So I don't know.
It's actually pretty. I mean, I do want to go to the interpreters again, but I mean, speaking of build root, I mean, I was surprised that stuff like Kismet, etc., is included in build root.
Oh yeah. Yeah, no, it has a decent amount. I mean, yeah. So it has a decent amount. Even on interpreters, it has a decent amount. It has full Python as well as MicroPython. But I mean, because if you're trying to build an embedded system, you want those debug tools. So I mean, that just happened to be also being used for security research. So it has a decent collection. But yeah, so on the interpreters, then really, so the problem is, I mean, like arguably, I would say that if I was, besides my biases, MicroPython is kind of the most popular, I would say, right now. But really, the problem I looked at trying to port MicroPython, and all of them are, when you port it, the first thing is like, well, where do you store your file system? So it wants you to make this flash driver, so because it wants you to be able to import. And it comes with all this baggage of trying to just port it, where if somebody else does that work for you on the board, then it's great, like the new Raspberry Pi. But if you're trying to port that, I think that's a kind of a non-trivial thing. So I looked at other interpreters that like, I just want to start out with an interpreter. And so eLua also I thought was, because there's a lot of Minecraft fans, and apparently Lua apparently I've been told that Lua runs in Minecraft, and you go to some terminal in Minecraft and then you could write Lua script.
I mean, Lua runs in a lot of places other than Minecraft, Josh.
Well, okay. So, some gaming applications. The only games I play are Civ 6 and the submarine simulator, which I'm blanking on the name. That's it. The extent of my gaming.
I mean, I got into, or the first place that where I was confronted with Lua was actually building OpenWRT. OpenWRT is Lua for.
Oh right, yeah, true. I mean, so that one is a legitimate option. Also looked at eLua, but again, it wants to bring all this file. So I was like, all right, I need an interpreter that basically starts from nothing. And there was two options, guys. There was Tiny Scheme, and there was this random fourth that this one guy wrote. And I was like, all right, so Tiny Scheme I got going actually first, to be honest. And that one I was like, oh, this is actually pretty nice. But then I'm like, then I had to be honest with myself. And I was like, Josh, not many people like the parentheses. And I was like, okay, fine. So then I was like, all right, let me fourth. I know Hackaday. So Hackaday has published several articles in Forth. So it's like a thing. And the other thing is it's really geared to engineers. So if you probably grew up, I mean, going through college, whatever, I always had an HP calculator. So it's this concept. I mean, Forth is very easy to describe. So it's a reverse Polish, basically it's a postfix notation. So like reverse Polish notation. So if you use the HP calculator, boom, you already got it. It also is stack based. So there's hardly any variable declaration. It's just all stack manipulation. And then the only other thing you need to know is that everything's delimited by white space. So, and if you have a token in the interpreter, you put a space, that interpreter then is going to token it. So, I mean, that's it. Those are like the rules of Forth. And then you can get going. So from the heart.
May I add that this sounds way worse than it is in practice? I mean, the learning curve is not that bad. Trust me. I'm not a language snob like Josh is.
Right. Yeah. So it's but I mean, so from a hardware point of view, so again, it's not just me. You can look at Hackaday articles where they talk about this. Why this is epic is because a lot of times you want to just hit registers, and especially if you're trying to write a driver, you don't necessarily know what it's going to do. So if you did this in C, be like, all right, do this program, print it out. Okay, do this, print it out, and then it's a compile loop. Here, it's like, all right, write a 1 to this address, enter, and it's like, oh, the light just blinked. Okay, cool, I got that working, right? And then it's like, I mean, the liveness of it is pretty epic.
No, but with a Linux driver, it might be as bad as something crashes. I got to reboot the system and then run
true.
Compile, load the module again, and then run my test again, right? I mean, so that's the advantage of having an interpreted language, which is, I mean, on top of it, it's running on a separate CPU because thanks to the Zinc, even though it's on the same hardware, so there's no way to crash this thing. and you're actually toggling I/O.
Yeah, and so I mean, if I was like, because another thing I see is a lot of hardware engineers that are in charge of board bring up the first time, I would totally be doing forth and just being like, guys, hey, software team, I made all the bits twiddled and I was able to push the data. Guess what? It's now your problem, right? And then you basically can keep this too, because this forth that I found was made by a hardware person, because the reason I know it's in one file, that's how you know what a hardware file see. It's if it's in one file, right? And then there was a compile flag to make sure it compiled in like C99. That's it. Like if you try to do any advanced, I tried to put in
the best C.
Yes, I tried to comment something without using the slash asterisk, and it's like, nope. It gave me an error. Wouldn't let me compile. That's the default. So I was like, this guy, he's a hardware guy. So I mean, if you were doing hardware bring up, this would be perfect because you never have to change the code. All you have to add is peek and poke so that you can directly hit the registers. And then that's it. That's the only C you ever have to do. And then you're done. That's all the C you have to learn. And then, I mean, this is it.
So I kind of feel like we're obligated to bring people back. I mean, so this is exactly what you find yourself doing if you're ever bringing up a board or you're trying to escape Arduino, the Arduino IDE. You find yourself writing ones and zeros to random registers and then seeing what the result is. So having an interpreted interface that lets you do the same just means that, you can run it without recompiling and see what the result is. And then hopefully eventually you get the correct result.
This is all true. That's a good summary. I can keep geeking out about how great Forth is, but that's probably the important takeaway.
But yeah, I mean, so like people inevitably, I mean, whenever you're doing anything, like I said, sniffing hardware, interfacing to hardware, you find yourself running ones and zeros. And so how do you do it? So it turns out with an interpreted language like this, I mean, you're not, I remember writing assembly to do the same stuff. I remember writing C code to do the same stuff, and none of it is pretty. I mean, some would argue Forth isn't pretty either, but I mean, it has other advantages like being interpreted, etc. No, but I mean, all jokes aside, I mean, it is pretty epic to just be able to toggle, have essentially an interpreter in which you can toggle I/O directly, just to verify that stuff's working.
Yeah, no, it's pretty fun. And then the other thing we're going to, so there's two aspects of it here. So the other thing that we are going to have for the class is the ability to kind of simulate this with Pulse View. Right. So before you get onto, so we're going to be using Pulse View as the main kind of GUI for looking at waveforms, because that's, I think, there's been a lot of work on Pulse View and there's been a lot of improvements to that. And so now with this, you basically can write this, practice the waveform, practice the bits you were going to send on x86 into a simulated environment, see the waveform, and then when you take it down to the board, you can have a lot more confidence that it's going to work. Even though it's going to be happening live, what you're saving, it kind of working in this Pulse View setting that we're going to make for you is it's just going to be like a much more controlled environment. So you'll have a lot more confidence when you're starting to toggle bits that it's actually doing what you want. So that's another aspect there. And then the other thing that we're going to so those are like the low level ones, but also because of the Linux side, there's going to be the opportunity to load the Linux image, and then you just kind of swap out the brains of the Zinc by putting in a different SD card, and then you'll be able to try these drivers from Linux as well. So for this iteration of the class, if you look at the site, I mean, basically the hardware requirements are the Zinc board. You need a reader writer, a micro SD, and then there's two PMODs, which I don't know if I have enough time to go into my PMOD Venn diagram of how PMODs and Zinc and Forth are all coming together, but the PMODs are essentially digilents. I try to bring everything into the universe of Josh, and everything basically anything has to all have every aspects of things that I like, which sometimes limits what I can do. But what PMOD is, besides being this epic interface, which I'm biting my tongue not to go into too much, is an easy way to add external ICs to the Zinc. And so for this version of the class, the two PMODs are a I2C based real-time clock. So that it acts like an EEPROM. It has a real-time clock, so we can use it for Linux as a hardware clock, and then also read and write to it directly. The other thing is a SPI flash that again we'll be able to use from Linux using SpyDev, but then also being able to directly access it. So those two external ICs for this version of the class, those are going to be the hardware requirements for this class.
Right. I mean, and so eventually the hardware requirements might change slightly. I mean, just in terms of we might try to implement more stuff just directly within the FPGA, but which will be even more epic because then it'll be even closer to the Venn diagram of what the Spearf1sh is.
Yeah, true. So I mean, there's nothing stopping us from doing it. It's just the time. So that for this first round, we're trying to get everything for this first class. So it's just a little easier to stick with the existing ones. And plus, the benefit of that is, at least when we do the Linux examples, they work well with the Linux environment. So, for example, especially on the I2C one, it basically seamlessly works with I2C get, the I2C tools, which Spearf1sh will have the I2C kind of hack. Basically, I2C tools package, which lets you read and write different I2C commands. And then that also works with the hardware time. And then we get to talk about device tree a little bit. So there's on the Linux side. I mean, so we're really kind of, so in this one, we're really covering, you're going to be really hitting the bits at the low level, but then you kind of get exposed to a little bit of the Linux side too, and see how that gets boiled up into higher level abstraction. So I think you're really going to get a good sense of, for any hardware protocol, not only how do you toggle bits on the wire, but how it actually plugs into an operating system, because you'll see both of those in this class.
No, I'm pretty excited. I mean, to be fair, I mean the kind of the gap, or like the amount that we have to implement to go from pulse view to running it on the hardware, I mean, is pretty epic. I mean, like if I could have had a waveform simulator, I mean, if I could have simulated what I'm going to have over the wire, like reliably before, I would have, I mean, that would have saved so much frustration, because then it's like, I mean, basically in hardware, 90% of what you're doing is you're saying, let me run whatever the run is, like, let me run this Verilog code, let me run this C code or whatever, let me run this binary, and then let me see what happens. And as is typical for hardware, nothing happens most of the time. I mean, so, and then why does nothing happen? Then you get the oscilloscope out, you get your logic analyzer out, you start analyzing it, you start looking into it, and then you figure out, well, it's not, the speed is off. I mean, like typical things that happen is the frequency at which I'm sending the data is way off, so I misconfigured this register. Or like I'm sending 6 bits instead of 8 bits or something along those lines. And so the fact that we can actually simulate this and let you play around with it and actually kind of speed up the turnaround, making sure that people are writing the correct signals and then actually running it on the hardware makes it kind of epic for, I mean, teaching the basics. Like, I don't know. I've never seen anyone else do it in a similar way where, it's starting, it's like verifiable before you run it for the intro course. I mean, I'm kind of spoiled with the FPGA stuff just because, I mean, one of the coding styles is to simulate everything. And so there's nice simulators there. Admittedly, you're writing Verilog code, which is like its own world. I mean, which is kind of requires its own class to get into it. Whereas here we're writing an interpreted language, and I really do feel that somebody who's brand new to hardware can actually toggle the bits and write the ones and zeros and see the result.
Yeah. So I mean, yeah. So we've been pushing 50 minutes now. I mean, there's a lot. We're doing the
classic. We're doing the classic podcast thing where we start off with the first iteration of the podcast. It's not going to go longer than 30 minutes. And then
yeah. No, I mean, I think this class in particular, there's a lot. I mean, we could easily keep going, but we should probably cut it. But I mean, I think it's just, I think we're both super. I mean, this class is gonna be super fun. Like I've given on that, like I'm telling you, the fourth thing is, don't be scared about it, because I gave it to one of my employees to try, who's still getting his like hardware chops on a little bit more, and it's like he like picked it up super quick. I mean, it was like, this thing's super fun. So, I mean, the way it's going to be very much geared to toggling bits and stuff, which is going to be pretty fun. So, I mean,
and the other thing that I mentioned is, I would say unanimously from all the clients that we talked to, this is the course that everyone's been asking for. Is We need to onboard even more engineers to be able to do hardware stuff. But our issue is they, had Java in school, like Josh mentioned at the beginning, or something along those lines, and so they've never actually toggled the ones and zeros. And how do we get them to the point where they're actually toggling ones and zeros, understanding these protocols, etc.? So I'm also very excited on that note that we're kind of lowering the barrier to entry for people who are completely new. And so I'm excited to hear the feedback from everyone, the feedback from the ever-growing fourth community.
Yes. I don't know. With me in those communities, though, I kind of like it's like the Marcho Grouch thing. It's like I don't know if I would join any club that would have me as a member. So I went to the because I looked up. There is a fourth interest. They call it the FIG. Oh, that's my phone. And it's like the fourth interest group. And I watched some of they've made the jump to YouTube, and I did watch it, and it was like, okay, this is good, but I don't see probably not going to join the FIG anytime soon.
Is it a yearly membership, annual?
Yeah, I don't know. It's like one of those things like ham radio where it's like I have I do ham radio stuff. I like it, but then it's like every time I get involved in one of those things, it's like I don't know. This is one of those. It's just like I don't know. It's like this. We think it's always going to be more than it is. Like you think you'd meet all these fourth people, and you was like, oh, these people are going to be so epic. It's like as you would think of someone who talks about fourth, obviously. And then it's like maybe.
I think they come full circle on the ham guys. I mean, you realize that you're 20 years younger than everyone else in the room. You're not exactly a spring chicken, Josh.
I know, but the ham guy, you would think the ham people would be liking fourth too. There would also, I can bring fourth into the ham, and then that completes the Venn diagram. That's the only piece that's missing. I can send my radio bits over fourth. This is it. I'm good.
But yeah, for sure. No, and I mean, just to highlight it one more time. I mean, so we're serious about. I mean, like I said, is kind of it's funny, like retelling it. I mean, I'm surprised when it dawned on us that we have Linux running on a platform that meets our criteria for everything that we do and that we teach people. We were kind of blown away because it's like, why don't we Linux all the things? So I mean. I expect great things, everything from toggling stuff over MQTT and other types of internet queues to, controlling my IoT at home. I mean, would all be epic use cases that we can now do.
That's true. If you Python 3 is available on Buildroot, if you could spare the extra 15 megabytes. I mean, if you got the dollars to spend the 15 megabytes on the SLC memory, then you can download Python 3, and then pip, you can actually that's also built in the build group. So from there, you've got pip, you've got Python 3. I mean, you've got the Spearf1sh. Then I mean, yeah, you can probably combine all this stuff from there. So I mean,
but I'm sure people in the comments /DMs. I mean, what's the memory footprint? I don't think he said for all of them, because I think that will come up.
Oh, on the so that was the issue. I mean, the Microblaze,
hardware engineers will want to know this one for sure.
Yeah. So I felt a little bad because I gave the Microblaze 256 kilobytes of memory. So I felt like I was asking for a lot. And then the fourth, I think the dictionary. So that's like so basically the dictionary is how much is built into the language. I think I'm almost pushing like 1.5K on that thing. So I feel like I don't know. I don't feel like a hog at that 1.5K dictionary. So that's basically how much. What was the
footprint of ELUA and MicroPython?
I mean, so MicroPython will run. So MicroPython runs on that STM32F4, but I think that thing is pretty big. I think the F4 is pretty
big, isn't it?
Yeah,
it's like 768 at least.
Yeah, and I think the issue is that it actually requires the code space. I mean, so it basically is assuming that you need a flash, which I think that chip has like a meg or something crazy, right? So I think that's really the issue, is that the RAM requirements are, I think, not as bad, but the code space size is, I think, significant in MicroPython. ELUA, I think, is actually pretty good, but again, the issue there was I didn't see a way to port it without having to like implement a flash drive. Like because they all assume you're going to, first thing you're going to do is like import a file. And it's like, guys, why? I have everything I need in already in memory. Like I'm busting at the seams at the 2K limit. I can toggle all the bits I need.
I mean, you wanna type it on your clickety keyboard, like back in the day.
So this is the best. I mean, so this is
Venn diagram, circle.
This is all right. Oh, my camera. I got so triggered. I turned off. My camera got overheated. This as what's going on. So we'll just have to. You'll have to
look at Dimitri laugh at Josh.
You'll have to look at Dimitri as I reset. Okay, so this is how great this fourth I found is, because this is how you could tell. Another reason you could tell it's by a hardware person. I should be coming back here in a second. I gotta pause. For okay. Here we are. All right. So this is how you can tell. So in a normal interpreter, here we go. In a normal interpreter, you would think you could write the entire line and then hit enter. Okay, that would be the expectation, but not in this version of fourth, because obviously what you want to do is have it interpret immediately. So the second you hit a white space, that thing gets interpreted, and the only reason that can happen is because it's this postfix notation. Because essentially the syntax won't change. So the second you hit space on whatever you're trying to do, boom, it just got interpreted. So you can't even mess up. There's no line editing, because obviously what you're entering in right away is immediately affecting it. Doesn't even have to wait for a carriage return.
I think we should end it here before we have to get into carriage returns.
Oh man, I could go on a rant.
No, Josh, we're ending it.
All right. It's a thing, though. I'm telling you, it's a thing.
The carriage returns.
Yes.
So yeah.
All
So
right.
anyway, so we'll link our GitHub if you want to check out Spearf1sh. We'll probably set something up where if you want to hear more about Spearf1sh, we'll at least set up some sort of mailing list that you guys can check out. So we'll have that set up for you. The GitHub as well. If you want to check out the courses, they'll be in the description as well. And then we'll also because somebody did DM me about this. We'll add a code for you guys that are watching the YouTube, so you can use code Spearf1sh for 10% off of any of our upcoming classes. So if you're watching this here and we have you excited and you're still looking to get into hardware, then the course will be coming up in just about 2 weeks from now, 2 weeks time. So you can hop on, get a 10% discount, and join the rest of the people that are already signed up.
But if you spell it with an I, you'll have to pay a 10% premium. So remember, it's with a 1.
I don't think we're doing
that. It depends on how many carriage returns you put at the end. So we'll parse it.
It's fine. Carriage returns are a thing in embedded.
All right, fine. We'll be nice. All
right. Wave out.
Slow wave. Until next time.
See ya.